Hi, everyone. Hope you are doing well. So, this week's screencast or this week's lecture is going to be broken up into two screencasts again. Again, trying to keep things around the 25-minute mark or so. So, this week, let's talk about some common statistics used in epidemiologic studies. And we'll get a chance to practice some of those this week. Now, one thing you've seen from the papers throughout this term is that we present a lot of data in epidemiologic studies. And these can be very dense, data rich manuscripts. And I think that's what really makes them kind of exciting is just all of that stuff you can dive into. Now, data exists either as numerical or categorical variables. Numerical variables, counts like the number of children per an age group, or different measures like height or weight. And then categorical variables, these result from classifying. So, for example, categorizing people by blood type. Do they have A, B, O, or AB? Lots of tables and graphs. Purpose is to display data in a way that can be quickly and easily understood. So, because the data is so dense, having a table or graph really brings things to life in a way that makes it more, like it says there, quickly absorbed or quickly understood. Each table and graph should contain enough information so that it can be interpreted without reference to the text. Titles should be carefully crafted to describe what the numbers in the cells represent, how the cells are classified, and where and when the data was collected. So here's an example of a table from an article by Smith et al., published in Medicine and Science in Sport and Exercise. And this shows data from looking at a population of Division I athletes who performed the Y balance test. And I'd like to highlight this here because the Y balance test was created by a Rocky Mountain University graduate. So here is a breakdown. Now, this was an epidemiologic paper trying to see if there were scores associated with test performance, or let me rephrase that. Were the scores from performing the test, were they associated with a greater risk of injury? So before they even got to that part of reporting what the risk magnitude was based upon test performance, you can see a breakdown of the injured versus uninjured individuals. So the descriptive data here are this demographic data. And what's interesting is only age and anthropometric measurements were significantly different. The asymmetry scores weren't significantly different. So that was kind of an interesting finding there. Even though they did go on to report that asymmetry, there was a greater risk. Here's something similar that I did with my volleyball study, or one of my volleyball studies, and presented all the athletes. And then I had a couple different comparison sections. Volleyball athletes who were not injured during the season and volleyball athletes who were injured during the season, and looking at them side by side. And when you look at them in this way, there weren't differences. Kind of similar to here. There weren't differences, right? But then when we take a look further at risk profiles, so in this case, the risk profiles were performance on the 3 different jump tests, then significant differences were presented. So this is, I think, really important to, sometimes you might only see something like this in a table where there's the breakdown between the injured and uninjured. But this really brings it to life differently where somebody's able to go, wow, okay, I can see what the referent or the reference group was, what their scores were, and they're quite similar to the non-injured individuals. But look how low the scores were for those who did get hurt. Here's Plisky again, the creator of the Y-balance test. His first study that he did at Rocky Mountain University was utilized the STAR excursion balance test, which went on to inspire the Y-balance test. Here's just another example of presenting data and doing so by grade and other factors, comparing boys versus girls. We've seen big tables like this before, and here we're able to highlight, like for example, looking at basketball for men, basketball athletes for all levels of collegiate play. We can get an idea for injury rates and those that are non-time loss in nature, those that resulted in time loss. Bar graphs, think about if you're looking at injuries throughout the entire body. So here were the injuries for female high school athletes. And it gives you an idea. Wow, it looks like the knee and the lower leg were major areas. Over 50% of injuries occurred there. It really, again, brings it to life. As somebody reads the text, they could find that, but this really makes it pop. Things that could be presented in an epidemiologic study, but more than likely not in the things that you and I, what we might do. Spot maps and rate maps. These display geographical locations of cases or rates. And this was one of those examples that talked about the first week, John Snow doing this to look for cases of cholera and then identifying how it was occurring around a particular water pump. There are rate maps examples, and you can find these online. A lot of times you can find things with the CDC website. And again, when we talk about epidemiology, it's not necessarily just disease, but here in this case, something a little bit more morbid, intentional homicide rate. And you can see with this rate map example, where are those hot spots at? Where are places that are potentially less safe to live in or to travel to? Really kind of a fascinating presentation there. Something we saw frequently during the COVID-19 pandemic, seeing cases like these heat maps or these rate maps showing where cases were elevated. And it was always kind of interesting because you would see not only the hotspots in major metropolitan areas, but also as you looked at different locations and were able to draw kind of analyses based upon the level of restrictions or requirements they had for their population. So again, here is a presentation from whenever I did a snippet of this, cases in the last 7 days. Here's cases per 100,000. So it just kind of illustrates different ways of presenting the data. Here's something that if you were involved in health and wellness could be of interest to you. Now, I don't have this in, let me put it into play mode. I don't have this in play mode, the PowerPoint, because I'm going to be going out of it soon to go to OpenEpi, but let's show this here. So this is really kind of an interesting one because what should occur is it should transition, and you can see that now transitioning from year to year to show changes in the prevalence of self-reported obesity. And so it's kind of interesting because one, here I live in Oregon and we're in the yellow, the 25 to 30%, but then there's 1 year that it jumps up. So it's like, why did it jump up and then go back down in 2015? That's kind of an odd thing. And then you can also see kind of a progression over time where as we start in 2011, there's some states in the South that are really high, but then we start to see this greater increase to occur. And so you start to wonder, okay, is this a factor of doing a better job of getting people to report? Or is this a factor of changes in exercise and diet behavior? Line graphs, very common. This is one from Mitchell Rao et al., one of his papers looking at people with their initial injuries during the season. So presenting injury rates, initial injury rates during the first month of the cross-country season, and seeing where there is potentially more injuries occurring. We see that increase, and it appears that potentially week 3, if we're just looking at this particular map, that week 3 was an area of significant increase. Can't say for sure because we don't see that information presented within the data, but we do see, for example, boys in week 2, there were 5 injuries per 1,000, moving up to about 10. Females, there were 10, moving upwards of like 18 or 19 in week 3. Here again from Agel et al. Showing injury rates over time, and it's always interesting, like what caused that drop in 89 to 90. Was this something to do with how recording occurred? Like what was the reason? So these create more questions and potentially lead to more research, but it's something that should be discussed within the article. Pie charts from one of our prevalence studies looking at the presence of preseason patella tendon abnormality, and 66% of the people did not have any ultrasound evidence, but then we can see that there was 35% that had one or more. Actually, 34%. Let's do the math correct. Histograms, organization of a data set into contiguous mutually exclusive intervals so that the number or proportion of observations falling in each interval is apparent. So histograms here showing, in this particular example, percentile ranks at Smith Elementary School in mathematics. I couldn't find one from many of the articles that I like to look at, so this is kind of the best I could come up with, but again, it's another way to show or present data. All right, let's look at calculating rates. So we like to report rates in epidemiologic studies. What percentage had the condition? We looked at ways to report rates, or we talked about rates previously. We might report them as like the rate of injury was 10 per 1,000 AE, or 1,000 athletic exposures, or something like there were 3.5 cases per 10,000 residents. So we usually utilize some number like 1,000 or 10,000 as a comparison number. Like, would you say there was one case per 100,000? Well, there might be times that you might say that. That might show the rarity of a condition. A lot of times for sports situations, they're going to show it per 1,000 athletic exposures. So what if you have a team of 20 athletes and they participate in 100 athletic exposures, so 100 practices or games each? Well, you can start doing the math there and seeing how many athletic exposures the entire team is subjected to. And I presented rates before. This from a basketball study comparing rates of injury in starters versus non-starters. So we've got the initial and subsequent injuries there. So the initial injury were the injuries that were the first injuries sustained by a particular athlete. So if we look, there were 18 initial injuries, and then there were 11 subsequent injuries, meaning one or more athletes had an additional injury. So now's your time to go to OpenEpi. So pull up OpenEpi. There's a link there that you can get from the PowerPoint, or you can just put OpenEpi into Google and it should come up. And then what we're going to do is go to person time. So let's find that now. Actually, I'll move forward a slide. going to go to Open Epi and go to person time over here. There's a 1 rate and 2 rates. Let's go to 1 rate first. And then so that I am, what you should be doing right now, probably the best way to do this is to have the screencast up and rolling, and at the same time have your PowerPoint up. I'm going to bounce back and forth between the two. So let me go to the PowerPoint here. I know I have a bunch up there because I've been working on a lot of different things today. So what you'll do is you'll click Enter New Data, and then we're going to put in these numbers here. Number of cases, 18, and person time, 6558. So person time here, that is your total number of exposures, or what you're interested in. So you're not going to put in 1,000 or 10,000, but you're going to put in the actual number you counted. So for example, if I had 20 athletes and they did 100 practices, then there's going to be, 2,000 athletic exposures. That's my person time in this case. That's what that means. Or if you followed 30,000 people for 1 year, your person time would be 30,000. So in this case, our number is going to be 18 and 6558. So let's come back to here, enter new data, 18 and 6558. Then we'll come up here and calculate. And Open Epi then will do the calculation for us. Now you could do the math, but here it is, a rate of 2.7, and we can see the lower and upper 95% confidence interval. So I would report that the rate of, I'll say injury in this case, was 2.7 per 1,000 athletic exposures, with a 95% confidence interval of 1.7 to 4.3. So I was rounding those two up there. Now, what should you use? Should you use mid-P exact? Should you use Fisher's? Open Epi gives a recommendation. They'll always give a recommendation in blue, and that comes from the creators of the software. There are, as you can see, different tests. How much do you get into the weeds with that? Well, I guess if you wanted to become an epidemiologist, you would study that at a greater level. I could not tell you what the Bayar approx Poisson is. So what I would just report in a paper is there was 2.7 per 1,000, in my case, athletic exposures, and the 95% confidence interval again was 1.7 to 4.3. Up here, you always need to take a look at what's in red to make sure that it's in 1,000. Probably 95% of the time, it'll present it as 1,000, but there are times where it will present it as 100 or 10,000. Why it does that, I don't know. So moving through this, there was our answer. Questions on that one? So we just demonstrated that. Now let's do one more here before we end this particular example. So for this one here, we're going to do comparison of 2 rates. So back here, this is where I was comparing 2 rates. I was comparing starters versus non-starters. So it may be of value at some point in time to see if there was a difference in rates between 2 different populations, 2 different groups. This statistic is called a rate ratio. And so let me go to compare 2 rates. So come back over here, compare 2 rates. It'll pull up this, and then I want to enter new data. Next, oops, sorry about that. How about if we go with, let me see what the next one here is. Let's go with this 8 and 10, 22, 47, and 43, 11. Now, how did I know which column to put things in? First off, I'd have to define what my exposed group is. That's my at-risk group, the group I think that's going to be at a greater risk of disease or injury. The non-exposed group is the other group. The cases being the number of people, and then the person time from there. So cases being the numbers of disease, the overall person time. So if I go back to PowerPoint here and show this, here I was comparing the rates of initial injuries in starters versus the injury rate in non-starters. Why would I want to do that? Well, obviously, the study involved more than 18 people. I'm looking to see, is there a difference in the rate of injury in starters versus non-starters? In other words, I'm trying to see if starters, I'm hypothesizing that starters are at a greater risk of injury because maybe they play more during games. So now, let's do the math. To do the math, we've already plugged things in. Come back to here. We saw that number. There were 8 cases in the starters, 10 cases in the non-starters. Here were their athletic exposures. Everybody still with me? If you have questions, look forward to answering them online. Let's calculate. Now, what we get is breakdowns of the rate ratio coming up. First off, the first thing we're going to see is that there is not a significant p-value. Going with the more conservative p-value, the two-tail, at the 0.05 level, we did not achieve that. If I use the mid-p exact, 0.37. That's what I would report, or a 0.374, whatever the journal wanted. Now, what is the rate ratio? The rate ratio is 1.535, and here's our 95% confidence interval. So the difference between groups, the rate ratio was 1.5 per 1,000 person time units. But it wasn't significant, so it doesn't matter. But if it was significant, I might say that the starters were 1.5 times more likely to get hurt, or the rate was 1.5 times greater than the non-starters. What's nice when you do the 2x2, the rate ratio here, you can also get the rate in the exposed and in the unexposed. And so they give us 3.56, 2.32. If we go back to our PowerPoint, we can come back up to here and see that, hey, there it is, 3.6, 2.3, and then our 95% confidence interval and p-value over here with our rate ratio. So pretty easy to calculate those, correct? So again, here's that p-value, not significant. There's our rate ratio. Again, we would report the rate ratio is 1.5 and the confidence interval, but it's not significant. So 1.535 per 1,000. And then, of course, we see the rate in the exposed and the rate in the unexposed. All right, so let's pause here, and then we'll get the next one up and going in just a moment.